Welcome aboard, my dear JEE Warriors. This is your Captain Shreyas, and we are on the day 3 of our Noob to Sigma series on the Vedanta JEE English channel. I hope I'm audible and visible to all of you. And in day 3, in the physics part, we are going to do KTG and thermodynamics, obviously very high weightage, along with questions, PYQs, and the quick revision in a very beautiful manner. So this is your Captain Shreyas. Welcome aboard. And if you are new to the channel, please subscribe if you have not done that yet and like this video. Mark your attendance. That is your Guru Dakshina. Okay. Hi Niveda. Hi Vish. Welcome, Sugan. Everybody join in. I know it is Sunday. Some of you probably wake up late, take a break. But guys, barely 100 days left for JEE. If you are going to take a break, obviously your marks are also going to take a break. Every day is very critical, important. You have to improve consistently every single day. So it's time that you don't lose focus. Please push yourself. Don't be lazy. Okay. Do not say, I will do it tomorrow after 1 hour. It's okay. Don't give any excuses. Okay. Because we are not just doing it for your sake or just for, getting average marks, but this is for you to get 99%. Right. So let's begin. And yes, the main session is live on the channel. I hope you have liked it by now. 5th November, 6 o'clock, the Sigma high weightage announcement is going to happen. The session is live on the channel. Go to the live section and quickly mark your attendance. It's right over here. Just go to live. You will see Sigma batch launch. Already so many kids are waiting. I want you guys to mark your attendance, guys, because this is a big change which is coming for you. You're not liking for me, you're liking it for you. You're showing your commitment towards this, right? So go ahead, it's there in the live tab. Let's start with equipartition of energy, molar specific heats, where we talk about different types of gases, their degrees of freedom, and what kinds of examples we can get. Also, internal energy and the law of equipartition of energy, and finally Cp and Cv. So let's have a look at it very quickly. In fact, I'm planning to write it down for all of you in a very simple way. See, whenever you take a gas and you heat it, that particular heat causes some change in temperature, causes the thermal energy to increase. It gives some thermal energy and it changes the temperature. It basically changes your temperature. How much the temperature changes also depends on something called as the process. That process plays a very important role on how much heat will get converted into thermal energy and change the temperature. Because if it is constant pressure, it is different. If it is constant volume, it is different. If it is isothermal, it is different. If it is adiabatic, it is different. So every process has its own limitations or process by which it can increase its thermal energy. So in general, we can say that our heat is either I can put M into S into delta T, where this M stands for mass, Q is heat, S is basically specific heat capacity, specific heat capacity, and delta T is obviously change in temperature. But this formula, you generally use it for solids and liquids. Solids and liquids, where you can easily measure the mass in grams or kgs. But the moment you have a gas, then you use moles and you use N C delta T. So in this situation, N is nothing but the number of your moles, C is your molar specific heat capacity. Per mole, how much heat you need. Molar specific heat capacity. Molar specific heat capacity. Keep this in mind. Okay. So all these things are important. This is obviously for solids or liquids only, and this one is for gases. This is basically for your gas. Keep that in mind. So you will see that there are different types of C, and it depends on what is the nature of that gas. And there are obviously different kinds of gases like monoatomic, diatomic, etc. And every gas behaves differently because how much energy it can absorb, how much energy it contains depends on how the structure of that atom is, whether it is mono, dia, etc. Okay. Example, starting off with a monoatomic gas. So when you take a monoatomic gas, like say for example, we take helium, neon, argon, right? These are all inert gas elements, right? Argon, helium, neon, etc. In those situations, you will see these kind of molecules can translate in one direction, second direction, and third direction. The rotation is insignificant. So they have three translational, translational, translational degrees of freedom. Degrees of freedom are those independent movements that a molecule can have, which can possess energy or contribute in the energy of that particular molecule. Keep that in mind. So it has 3 degrees of freedom if you take a monoatomic gas. Similarly, if you take a diatomic gas, if you take a diatomic gas or a linear polyatomic gas, or linear, let's say triatomic gas, diatomic or linear triatomic gas. Diatomic means hydrogen, nitrogen, oxygen, like that. Linear triatomic is carbon dioxide. Their bond angle is 180 degree, just like you have 107-8 degrees for H2O molecule. It's a non-linear polyatomic molecule. Carbon dioxide is a linear polyatomic molecule. In such situations, you will see that those molecules, whether it is diatomic or polyatomic, doesn't matter. Okay, as long as it is linear, it has basically this had 3 degrees of freedom translation wise. This also has translational wise 3 degrees of freedom, but additionally, it also possesses rotational degrees of freedom like this, but it can't rotate like this because if it rotates on the axis, it does not contribute in energy, because if the axis rotates, it's hardly going to cause any energy. But when it rotates like this, it has some energy. So it has three translation and 2 rotational degrees of freedom. But in a very special case, it so happens that it gains extra 2 vibrational degrees of freedom. But there is a catch. This only happens at a very high temperature, like 1000-2000 Kelvin. Then extra vibrational degrees of freedom also contribute significantly in the energy. But for normal situations, you will only count 5 degrees of freedom. Extra 2, which will add up to 7, will only come at a very, very high temperature. Keep that in mind. Next, we have your polyatomic molecules, which are non-linear triatomic molecules. Non-linear triatomic molecules. Say, for example, H2O. It's a non-linear molecule. So in such situations, when it is non-linear polyatomic molecules, in such situations, it obviously can move in 3 different directions, but at the same time, it can have rotations in all the 3 axes, which contribute significantly. So it has 3 translational degrees, and 3 rotational degrees of freedom. Rotational degrees of freedom. Keep this in mind. Okay, everyone with me? All right. Having said that, each degree of freedom, the law of equipartition of energy says the law of equipartition of energy says that each degree of freedom per molecule per molecule has half kT of energy, where this K is your Boltzmann constant. This K is your Boltzmann constant, and whose value is R divided by Na. R divided by Na. So if this is per molecule, so the energy of a molecule, because it will have F degrees of freedom, F multiplied by half kT is the total energy of a molecule. But if you talk about the total energy of a gas, that will be nothing but the number of molecules in that gas into F into basically half kT into half kT. That is what it is. Now you can rearrange these equations and etc. all of that. You can say F is over here, then 2 is below. This K is basically R divided by Na, and this N comes over here, and T is over here. This N by Na is number of moles. So it will become basically N and then R and then F divided by 2. N by Na is number of moles. R is there, F is there, 2 is there, and T is there. This particular term becomes your specific heat capacity at constant volume. This is basically the internal energy of that gas. This is then given that symbol U, which is also called as internal energy of the gas. Internal energy of our gas, which is nothing but NCV into T, where my specific heat capacity at constant volume is R into degrees of freedom divided by 2. Keep this in mind, right? These are again very, very important formulas. CV is nothing but your RF divided by 2. Okay, perfect, awesome. Now, having said that, you can also get remaining relationships. You can also get remaining relationships for CP, CV, etc. So, if you ask me what is specific heat capacity at constant pressure, that specific heat capacity at constant pressure is whatever CV you get plus R, which is nothing but your gas constant. This is called as your Mayer's relation. Mayer's relationship. This is called as your Mayer's relationship, which you should obviously know. But if you take the ratio of Cp divided by Cv, that is gamma, which is also called as adiabatic ratio. Adiabatic ratio. This adiabatic ratio also comes out to be 1 plus 2 divided by degrees of freedom. Okay, this also comes out as 1 plus 2 divided by degrees of freedom. Using these equations, you can rearrange and you can write CV. We already know it is gas constant into degrees of freedom by 2. You can also write it as R upon gamma minus 1. And same way, CP, you can write it as gamma times R divided by gamma minus 1. Because CP is more than CV by gamma. You can see gamma is that ratio. So gamma is always more than 1. So that is why CP is always more than CV gamma times. And if you talk in addition terms, it is more by CV by a term of R. Okay, so these are some important relations which you should definitely know. All these things have been put over here also. All right. Anyways, having said that, let's talk about for monoatomic, diatomic, and triatomic. What are those values? Well, the number of degrees of freedom, like we saw over here, the degrees of freedom is 3. Here, the degrees of freedom is usually 5, unless you take a very specific case of vibration, then the degrees of freedom is going to be 7, and here the degrees of freedom is just going to be 6. So let's calculate every single thing, starting off with CV. CV is RF by 2. R into F is 3, So 3R by 2. Same way over here, the value of CV would be RF by 2 or FR by 2, 5 into R by 2. But in a specific case, it will become 7R by 2. I put a star mark. The star mark stands for high temperature, vibrational included. All right. In the third case, the value of CV will be FR by 2, 6R divided by 2, which is basically 3R. Now, if you go to CP value, CP is nothing but, I just told you, CV value plus R. So whatever you get, you add R to it. So this will become basically 5R by 2. This particular value will become 7R by 2, or for high temperature 9R by 2. Remember that. And in the last case, this will become 3R plus R, which is 4R. Lastly, we can also write gamma. Gamma is the ratio of Cp by Cv. So therefore, for monoatomic, it will be 5 divided by 3 because 2 and R will cancel. In this case, the gamma value will be 7 by 5 for normal temperatures. For high temperatures, it will be 9 by 7. Similarly, in this situation, this gamma value will be 4 divided by 3. That's it. So if you know these basic terms, you can easily solve many questions, guys. Okay. So I've explained it to you how this works and how to remember it all. Okay. All these things you should definitely know, guys. Okay. So I have kept it over here also and here also. It's now time to start doing some questions. This came in 2025. Yeah. Vibration has 2 degrees of freedom. Yes. One mode corresponds to 2 degrees of freedom because what happens is it can rotate, oscillate like this and also go like this. So it contributes to 2 kinds of energies, you can say. Okay. Let's go, guys. Solving this particular question. Ready for it? Yes, honey, Spidey, Hasvi, Shaurya, very good. Come on, guys. CR7, Ninjan, everyone, come on, spam the answer in the chat box right away, right now. Here it is. Triatomic gas. What is the value? Diatomic, monatomic, diatomic, rigid gas. Rigid means vibration is not there. Non-rigid means vibration is there. That's all. So if you talk about monoatomic, it will be basically 5 by 3. So monoatomic will go to 5 by 3. That's it. It has 3 degrees of freedom. It has basically 3 degrees of freedom. So you can find Cp by Cv, which is basically gamma, which is 1 plus 2 divided by degrees of freedom, which comes out as 5 by 3, as you can see, right? So that is how you can get gamma. If you talk about diatomic rigid gas, it has 5 degrees of freedom. So 1 plus 2 by 5, which is 7 by 5, that will go to option number 2. Yeah, is that right? Similarly, if you talk about a triatomic rigid gas, think about it, and diatomic non-rigid gas. The moment you have a non-rigid gas, yeah, the moment you have a non-rigid gas, what will happen? 2 extra degrees of freedom will come. So 5 plus 2 will make it 7. So 7 degrees of freedom will come. So 1 plus 2 by 7 will make it 9 by 7. So where is 9 by 7? It's right over here. So this is the fourth option, and obviously the last option will correspond to 3, 4 by 3. Triatomic rigid gas. This has basically 6 degrees of freedom. So that will be 9 by 7. Yeah. So A is going with 3. A is going with 3. So 1 or 2. B is going with 4. B is going with 4. So option number 1 is the right answer. Option number 1. Perfect. Let's go to the next question on your screen, and here it is. According to the law of equipartition of energy, the molar specific heat of a diatomic gas at constant volume where the molecule has one additional vibrational mode is how much? This again came in 2023, as you can notice. So molar specific heat capacity of a diatomic gas at constant volume, that means they are asking CV. So CV is R into F by 2. Now how many degrees of freedom are there? It is a diatomic gas. One additional vibrational mode is there. Lot of people got confused. What is this mode? A mode is basically 2 degrees of freedom. So actually there are 3 translation plus 2 rotational plus 2 vibrational, which makes it 7 degrees of freedom. So that F is actually 7, and hence the answer is option 4. Many students just thought 1 degree of freedom is there, so they wrote 3 plus 2 plus 1, and they wrote 6 degrees of freedom. And when you write 6R by 2, you will get the answer as 3R. It is not there in the option, but then they got confused. Is the question as a bonus or something? Yeah. The cap for the captain, Azad. I think Spidey mentioned it. Right. Perfecto, perfecto, perfecto. Amazing. Let's go to the next question on your screen. Like you can see, these are all formula based. Let gamma 1 be the ratio of molar specific heat capacity of Cp and Cv of a monoatomic gas, and gamma 2 similar ratio for a diatomic gas. Both of them are rigid. So gamma 1 by gamma 2 is how much? All right, let's see. So gamma 1 is basically for a monoatomic gas. Monoatomic gas has 3 degrees of freedom. So gamma 1 will be 5 by 3. Okay. Now, if you talk about the next one, which is gamma 2, that is for a diatomic gas. A diatomic gas has 5 degrees of freedom. So gamma 2 will be nothing but you have 5 over here and 7 on the top. Now, the question says you have to find the ratio of gamma 1 by gamma 2. Gamma 1 is 5 by 3. Gamma 2 is 7 by 5. So it will become 5, 3 goes over here, 7 over here, 5 on the top. So this will become 25 by 21. Very straightforward. 25 by 21 is option number 3. As you can see, these direct formula types have come. Okay. And thank you so much. Gautam, means a lot. Yes, welcome, welcome, welcome. Thank you so much, Gautam Kishore. You should tell me where you are from, which city, which board or which state. I would love to know about you, because everyone out here has formed so many bonds. They are sharing messages, they are sharing creatives, they are sharing, a lot of material. They are forming study groups. The moment you know, oh, you are also from Coimbatore, huh? I am also from Coimbatore. Let's meet. Let's make a group. Let's study. So I want everyone out here to share, collaborate, join hands, and crack this JEE together, guys, because this JEE is going to be one crazy JEE. Let me warn you in advance, because the NTA has been acting very weirdly. Okay. And when somebody acts weirdly, that is a word of caution. The correct relation between the degrees of freedom and the ratio of specific heat capacity is, what's the correct relation between the degrees of freedom and gamma? I just told you sometime back, gamma is basically 1 plus 2 by F. 1 plus 2 by F. But we want F over here, so we need to realign it. So gamma minus 1 is 2 by F. Take the reciprocal. So 1 by gamma minus 1 is F by 2. Shift the 2 on the top. So it will become 2 divided by gamma minus 1. So 2 divided by gamma minus 1, which is option 1. Directly you can mark the answer. Is that right, everyone? Very good. These kind of questions have also come where they ask what is find the total energy of 3 moles of hydrogen with 2 moles helium. That kind of question has also come, where what you need to think is, if I want to find the total energy, it is the energy of hydrogen gas plus whatever energy is there of helium gas. Now hydrogen is a diatomic molecule, helium is a monoatomic molecule. That is something we need to keep in mind. So we will put NCV for hydrogen into T plus NCV, this is for helium, and into temperature. Number of moles for hydrogen is 3. Specific heat capacity for diatomic is 5R by 2, this into T, plus Moles of helium is 2. Cv for helium, because it is monoatomic, it will be 3R by 2 into T. And then you can see 3 into 5 is 15 and 2 into 3 is 6. Okay, so R and T are common, the whole thing divided by 2. So that would be 21 RT divided by 2. So that is the total energy of that gas. These kind of questions were also asked in 2024 and 2025. Right. Perfecto. Amazing. Is it enough to like get an, oh my God, King Cobra, how about this? You post the comment in the comment section. I will answer and reply to that particular comment. Next one is the speeds concept, the different speeds which are there inside a gas. By the way, I feel whatever lecture you are having today, it also saves the work for Diksha ma'am, because the same things are there in chemistry, thermodynamics. So by throwing one stone like Rajnikant, you are killing two villains. You shoot one bullet and that bullet is piercing through one villain and also going through the next villain. So that is what you are doing today. In fact, yesterday also, you have shot one bullet and it has killed two villains. Why? Because we did atoms, photoelectric effect, right? The concept of atomic structure, all these things, de Broglie wavelength, matter waves, everything is there in chemistry. So in a way, you have done double dhamaka, guys. You have done double dhamaka, and this is crazy. This is crazy. Okay, so moving on. When you take the molecules, atoms of a gas, they are moving randomly. Each molecule has different speed. But if you take the most likely speed, it will be different. The average speed, it will be different. The root mean square speed, that will be also different. In fact, if you see the variation of the speeds of the gas, they look something, I have very little space here, I will draw it here. They look something like this. It's called as the Boltzmann curve. So the curve peaks over here. Over here, you have the number of molecules. Here you have the speed. You will see most of the molecules have a particular speed that is called as the most probable speed. Very high speed is there with very few molecules. Very low speed is also there with very low molecules. So everyone has different speeds, but yeah, majority carry one particular speed called as the most probable speed. And the value of the most probable speed is nothing but 2RT divided by your m. 2RT divided by m. The average speed is given by root 8RT divided by pi m. R is gas constant, T is temperature in Kelvin, not Celsius. Pi is your constant. M is molecular mass, again in SI units, that means molar mass you have to give in kg per kg. Okay, everyone? Awesome, perfecto. Last one is your root mean square speed, the squares of all the speeds taken, then you take the average of it, that is the mean part, and then take the root. That's why root of the mean of the squares of the speed comes out to be root 3 RT divided by m. And you will see that the most probable speed is related to average speed to the RMS speed by this particular ratio, because RT by m is common. So root 2, root 8 by pi, and root 3. So this is basically that particular ratio. Most probable speed is 1, average speed is slightly more, RMS speed is even more. It has a higher comparative relative value. Okay, so these basic things you should know. It's time to solve some questions. In 2025, what has come? Consider the sound wave traveling in an ideal gas. All the three gases are given. All of them have the same ratio of P by rho, where P is the pressure, rho is the density, the ratio of the speed of sound to the gases. Speed of sound is asked, and you might be wondering what is it or how is it related to KTG. Remember, speed of sound formula looks very similar to the RMS speed and all these speeds formulas. So when you talk about velocity of sound, right? Velocity of sound in a gas, that looks like this. Gamma RT divided by m. Gamma is there. Instead of that number 8 by pi or 3 or 2, gamma, if you put, that becomes the velocity of sound after Laplace correction over Newton, which gives you the accurate speed of sound longitudinal waves in air. So as you can see that the velocity of the sound is basically gamma T divided by M. You can also replace it by gamma P by rho. There is a relationship, right? PM is equal to rho RT. So we have used that. PM is rho RT. Therefore, P by rho is RT divided by M. So RT by M has been replaced by P by rho. They all have same ratio of P by rho. That means the velocity of our sound is directly proportional to the root of gamma. So if you want to find the ratio, you have to take the ratio of gamma first for helium, then for CH4, and then for CO2. That's it. Very interesting question. Now this is mono, this is poly, this is also polyatomic. So guys, think about it. What will be the answer? Just try to substitute. Yes, just try to substitute, my dear warriors. What do you think the answer will be? Come on, everyone. Yep. What will the answer be? Come on, come on, come on. Everyone, spam the answer in the chat box. Spam the answer in the chat box. Spam the answer in the chat box. For helium, what will it be? Helium is a monoatomic molecule. So 3 degrees of freedom. So gamma will be 5 by 3. Okay. CH4, polyatomic non-linear. So 6 degrees of freedom. So what will it be? 4 by 3. Okay. Next, CO2 is a linear molecule. So it has 5 degrees of freedom. So therefore it will be nothing but 7 by 5. That's it. That is the answer. So 5 by 3, 4 by 3, 7 by 5. It is there as option number 2. Very good. Very nice. Not third option. Many of you got confused. You guys thought both of them are same. Yes, they both are polyatomic, but this is non-linear, this is linear. That is the big difference. Okay. Lot of students made that mistake. This is non-linear. This is non-linear, whereas carbon dioxide is a linear molecule. So it has different degrees of freedom. That is the catch in this problem. Many students make it. That's why it's a PYQ. Let's do the next one. Okay. This is on mean free path. Okay. Think of mean free path. Actually, I can discuss that concept in a bit. Mean free path is that average distance which a molecule will travel between one collision to the next collision. Let's say it collides with another molecule over here, and then it will travel some distance. That is basically your mean free path before hitting another molecule and going somewhere else. So that is your mean free path, guys. It might collide with some molecule coming from somewhere over here. It will go like this. Some other molecule coming from here might go like this. So between two collisions, what is the average distance? That is called as the mean free path. That is given to me. Also, the average speed is also given to me. Find the frequency of collision. So to go from here to here, some time will be taken. And it is going with some speed, let's say v. So we know speed is nothing but distance divided by time. So if I find out the time, that time will be nothing but lambda divided by speed. But the question is not the time, it is the frequency. So frequency is the reciprocal of the time. So the reciprocal of time will be velocity divided by the mean free path. Velocity is 600. Mean free path is 3 into 10 to the power minus 7. 6 by 3 is 2. Those two zeros are there, and 10 to the power 7 goes on the top. So it will become 2 into 10 to the power 9, but unit is hertz. 2 into 10 to the power 9 hertz or per second, which is the third option. Got it? Yes, very good, Nikita. Niveda, Gautam, it's not 2, it is 3. No problems. Mistakes will happen. Yes, it's me, Hall. Yes, it is option 3. It's not option 4, guys. Okay. Perfect. Shall we move ahead to the next question on your screen? Here it comes. All these are tricky questions. All these are laying traps. That is why you are here. The ratio of vapor densities of two gases at the same temperature is its velocity will be in the ratio of 4:25. The ratio of RMS, I think wording mistake is there. The ratio of vapor densities of two gases at same temperature is actually at same temperature is 4 is to 25. Then the ratio of RMS velocities. This is the actual question, I feel. Yeah. So ratio of vapor densities of the two gases is given. The ratio of RMS velocities is asked. Now you might wonder, how is this density related to the RMS speed? Well, if you go back a little bit, RMS velocity was root 3 RT divided by mass. And I just found out some time back that, wait a minute, using ideal gas equation, RT by M can be replaced by pressure by density. So why not write this down as root of 3 pressure by density. So vapor density is given and same temperature is also given. Then the ratio of RMS speed is asked. So guys, come on. Think about it. What you should do? RMS speed is inversely proportional. RMS speed is clearly inversely proportional to the root of densities. So RMS speed 1 by RMS speed 2 is rho 2 by rho 1. So rho 2 by rho 1. So rho 2 will be 4, rho 1 will be 25, the inverse ratio. This was rho 1 by rho 2, rho 2 by rho 1 will be 25 by 24. So root 25 is 5, root 4 is 2. So 5 is to 2 will be the correct answer, which is the third option. Got it? 5 is to 2. Yeah. Lot of people get confused. They write 2 is to 5. They forget it is reciprocal. They forget to put 4 by 25 as 25 by 4. Okay, this one was rho 1 by rho 2. Please keep that in mind. This will obviously be rho 1 by rho 2. So rho 2 by rho 1 will be 25 by 4. That is a common mistake. Moving on to the next question on your screen. The root mean square speed of smoke particles is how much at NTP approximately? K is also given. Wow, interesting question. K is given, mass of the particles is given. So what do we do? Because it feels like a very strange question. It is not fitting in our standard formulas. Now, again, root mean square speed is asked. So I'll go back to the formula, RMS speed. It is nothing but root 3 RT divided by our mass, isn't it? Okay. Now, I do not know the molar mass. So I have an idea. Why not write the molar mass as the mass of each molecule into the Avogadro number? That's what it is. If I tell you the molar mass of hydrogen is 2 kg per mole, it means if you take 6 into 10 to the power 23 molecules and if you add all their masses, you will get 2 kgs per mole. That is what it basically means. Okay, so what happens now? What happens now? This R by Na, right? Can you see? Can you see that R by Na? Yep, that beautifully converts into Boltzmann constant and you are left with just mass of a molecule. Capital M is per mole, small m is per molecule. That's the difference. Great. Now it's just a matter about substituting it. So we have 3 multiplied by 1.38 into 10 to the power minus 23 into what temperature will you put? Yes, NTP, so 293. Okay, and what else? M molar, this mass 5 into 10 to the power minus 17. Now, because we have calculators, we have the use of calculators allowed, so we can calculate it easily and we will get the answer. So approximately, say, yeah, calculators are allowed by NTA now, so be happy. Approximately, just see how much answer you will get and let me know. C, Paka, 15 millimeters per second. Very good. So 15 into 10 to the power minus 3 meters per second. 10 to the power minus 3 is millimeters. That should be the answer. Very nice. Moving to the next question coming up on your screen. Oh, that's on mean free path. I just discussed about the mean free path with you just some time back. It is basically the average distance which a molecule will travel between two successive collisions with other molecules. Every molecule will collide, it will go how much free distance it can travel. Now, this is one way of remembering it, which is very complicated. I would say remember this easier formula. This is much better. Lambda is equal to, you have volume of the gas on the top divided by, you have root 2 and then pi and then diameter of the molecule. D is the diameter of the molecule. It will be given to you square and then you have basically N. This is easier to remember, as you can see, as compared to this. This is easier. Now, if you use gas law and you write number of molecules in terms of moles and you convert it into Avogadro number and you use gas constant, convert it into Boltzmann constant, then you will get this weird relationship. But yeah, sometimes questions where temperature is involved, then you will need this. But if temperature and pressure is not involved, then 90% of the times this formula will help you. Okay, but yeah, you can always use your gas equations to convert it into this form. So if you want to convert over here, use PV is equal to nRT, number one. Number of moles is number of molecules upon Avogadro number, and Boltzmann constant is R divided by Na. Just using this, you will be able to convert it into this bad evil looking formula. Okay. Sir, please tell location in CBE. What are you asking? I didn't get you, Gautam. What do you mean by CBE? I'm not really sure what you mean by that. Okay. So it's time that we solve some questions coming up on your screen. Here it is. First question, statement based. There are two statements given over here. Statement 1, the mean free path of gas molecules is inversely proportional to the square of the molecular diameter. I think that is absolutely correct. As you can see in this formula itself, the mean free path is inversely proportional to the square of the diameter. Perfectly right. Yeah. Next, average kinetic energy of the gas molecules is directly proportional to the absolute temperature of the gas. Average kinetic energy. Kinetic energy is nothing but internal energy, and internal energy is NCV into T. You can see kinetic energy is directly proportional to the temperature of the gas. So this is also correct. Both are right. So both are right. Both are right. Both are true. That means option number 4. Sometimes both are correct is option 4. I have seen many students do this stupid mistake. The moment they get both are correct or both are false, they have there in their mind the first statement or the first option is both are correct and the last option is both are false. I've seen many kids do this. Oh, both are correct, sir. Option 1 I mark. Read it. Option 1 says 1 is false, 2 is true. So sometimes they can juggle, they can shuffle those options. So be very, very careful over there. Location in Coimbatore. Uh, you can check this particular website. I mean, as you're watching this video, it's very straightforward. You can go down. Okay. See, and you can go down, 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 down. Somewhere it will be, man. Huh. Check out the offline Vedanta center near you. It's there in the description box. Click on this particular link. Okay. And this is all the centers that we have. So somewhere here only, man, it should be. I also don't explore this much. Okay. Book a visit. Why is it showing Hyderabad? I don't want Hyderabad, bro. I want, my God. Looks like I have to get this description box changed. Thank you for pointing it out, man. Yeah. Vedantu Offline Center, it is there on the main homepage only. Just click on that. This will open up. And yes, you can choose your city over here. Wow, this is better website. Okay. From this, you can, yeah, go to whichever, yeah, center you want, like Coimbatore. And you can see it is there, Vedantu Learning Center in RS Puram. This is the Google Maps location. You click on it, it will take you to Google Maps. Yeah. So this is your Google Maps location. Yeah, that's where your Vedantu Learning Center is in Coimbatore. Okay, cool, fine. Yeah, all right. So moving on to the next one coming up on your screen. Here it is. If n is the number density and d is the diameter of the molecule, then the average distance covered by a molecule between two successive collisions. This was one of the easiest questions which came in 2024. Direct formula, many kids got confused because all of them look similar. Sir, I got fully confused, sir. I don't remember only. And then I'll tell you one more strange thing which happened over here, that it does not look like your original form. The mean free path, the average distance, that is basically the mean free path, is nothing but the volume divided by root 2 pi d square into n. Now you take that volume term below, so it will look like this, root 2 pi d square n by v. So what is this n by v? This is number of molecules per unit volume. They have used a special symbol for this, that is small n. So this small n that you see over here is basically number of molecules per unit volume. So like that, there is only one single equation, and that is the third one. Got it? Yes. Many students made a stupid mistake in this particular question. Actually, it was very straightforward only. Okay? Cool, guys? Shall we go ahead? Perfect. Let's go then. All right. So we have now come to work done by the gases and first law of thermodynamics, and also the different processes that we have. I think we should, yeah, one by one go to that. Okay. All right. So let's go to work done by the gas. Heat is done. Internal energy is done. Remember, just some time back, I told you about heat. In fact, that was at the start of the lecture only. Where is it? Heat. We spoke about heat in the first part, how it is related to the specific heat capacity and temperature. We also spoke about internal energy formula. The only term which is now remaining is work, and then we can go to the first law and the processes. Let's go, guys. We are on to thermodynamics now. So the work done in physics is always by the gas, not on the gas. That's a big change. So Diksha ma'am will use opposite sign of whatever I am using. Please understand that. So for me, if a gas expands, for a physics teacher, I will say the gas is doing positive work, but chemistry teacher like Diksha ma'am will say the work done on the gas was negative because the gas has expanded. Okay, work done on the gas is the term used by chemistry teachers or in chemistry subject. By physics teacher, it will be work done by the gas. So for physics, expanding is positive. In chemistry, expanding is negative. So think it's opposite in chemistry of the natural way of thinking. Okay. So work is integral of PdV. Integration of PdV is going to give you the work, which is also the area done, area under the area under the pressure versus volume graph. Pressure versus volume graph. Keep that in mind. If it is positive, it is expanding. If it is contracting, it is going to be negative. Oh, Gautam, right now I'm in Bengaluru. That is our head office where we are. Yeah, right now I'm in Bengaluru. Most of the teachers are working from there. All right. Moving on. Moving on. Now, once you understand this, we'll talk about the first law of thermodynamics, which is whatever heat you give will be converted into internal energy and also in performing work. If I drink something, I gain some calories, that is heat, because of which I'll become strong, I will gain some energy. So I've gained internal energy. And I will also lift objects. I will also do pull-ups, push-ups. I'm doing some work. So whatever energy drink I have, that will increase my energy, and I will also do work. I'll push, pull things around me. Is that right? So that is the logic behind this energy conservation equation, which is the first law of thermodynamics. All right. Now, standard conventions, guys, work done is positive. That means it is expanding. Work done is negative, means it is contracting. Heat is positive, means heat is given to the system, it has absorbed. Heat is negative, means it has released it. It has given out that heat. Simple. Okay. All right. Now let's talk about the different processes which we have, and then we'll go to some questions. First one, let's say isochoric process. It is easier to first discuss. All the processes, delta U, work and heat, and what is the graph and what is happening, you should know. Okay. Starting off with isochoric. Isochoric means volume is constant, If volume is constant, pressure will be proportional to the temperature in ideal gas equation. Because volume is not changing, it is not expanding nor contracting, so work done will be neither positive nor negative. So the only option left is 0. So on a graph of pressure volume, that graph will go straight vertically up because volume will not change. Yeah. So in that graph of pressure versus volume, it will look something like this. Okay, volume is not changing, no area. So whatever heat is there, which is delta U plus work is only not there. So all the heat will go in increasing the internal energy. So if you supply heat, everything will go in internal energy. And if heat is released, everything will come from the loss of internal energy. So delta U is NCV delta T because U is NCVT. So because U is NCV into T, delta U will be NCV delta T. Keep that in mind. That is what the formula is. Now, if you take a isobaric process, that's where pressure is constant. So if pressure is constant, then the volume will be proportional to the temperature by ideal gas equation. Now, in such situations, you will see that the graph will be again a straight line, but this time it will be horizontal. That's how it will look like. And the work done will be just pressure into the change in volume because pressure is constant, integral. I don't have to do any integration in a way. So it will just be the area under this graph, which is very easy to calculate. So it is height into the width. So height is P, width is V2 minus V1, which is the area of the rectangle. Heat will be delta U plus work. And remember, heat is NC delta T, but C in this case will be Cp. So that is why Q will be NCp into delta T. Work will be P delta V. Delta U is still going to be NCV delta T. Even though it is isobaric process, remember U is always NCV. Okay, always V will come for U. Keep that in mind. Keep that in mind. But heat will always change depending on the process because this was isobaric. That's why it became Cp. If you see the previous one, in the previous one, Q became NCV delta T. Coincidentally, Q and delta U became similar. Okay, keep that in mind. Then the next one, isothermal process. Temperature is constant. Temperature is constant, so pressure is inversely proportional to volume. So in this case, the graph of pressure versus volume will look something like this. The graph will look something like this. The work done will be nRT log of V2 by V1. Because temperature is constant, delta T will be 0. So delta U, internal energy, will not change. It will be 0. So whatever heat is there will completely go into work. Remember, heat was delta U plus work. So delta U is not there. So all that heat will completely go into work. Okay, that is for isothermal process. Yeah, thank you for all the love, man, from Sri Lanka. I want to visit Sri Lanka, man, but I'm not getting time. I'm really planning to visit Sri Lanka very soon. I love seeing some reels from Sri Lanka, beautiful beaches. I want to see candy and everything. Hopefully, we should have some nice meetup in Sri Lanka because I keep seeing our channel analytics. A lot of kids out there from Sri Lanka. And even when I was in NIT Nagpur, I had so many friends from Sri Lanka because NIT is, welcome students from all our SAARC countries like Nepal. So many people from Nepal were there, so many people from Bhutan and even Sri Lanka. It's lovely to have you guys out here. Okay, a thermodynamic process. Okay, what is this? Adiabatic process. A thermodynamic process where heat is not exchanged. So Q is 0 in this case. So because Q is 0, think about the first law of thermodynamics. Heat is delta U plus work. Heat only is not there. So delta U plus work is 0. So that is why delta U is negative W. That is easy way of writing it down. Whatever internal energy is changed is negative of the work done. And in adiabatic process, PV raised to gamma is constant or TV raised to gamma minus 1 is constant or P raised to 1 minus gamma into T raised to gamma is constant. You can use this for finding pressure, volume, temperature when it is expanded, compressed, whatever is happening. So whatever delta U is there, the negative of that is the work done. Easy formula is P1 V1 minus P2 V2. divided by your gamma minus 1, and you can also use nRT T1 minus T2 by gamma minus 1. Okay, so both these formulas are one and the same thing. Any of these you can use, right? Pakka? Done? Dusted? Shall we go ahead, guys? Shall we go ahead and solve some questions now? This was our adiabatic process. Keep this in mind. Let's solve some questions, and here it is on your screen. If dq and dw represent the heat supplied to the system and the work done on the system respectively, then according to the first law of thermodynamics, dq, I think some symbol problem is there. Some symbol problem is there, guys. Somewhere plus was there. I don't know where that plus was. So I'll just correct it and paste it properly in the PDF with the solution. So ignore that question. I think some symbol mistake was there. Anyways, match the following has come almost every single year. So processes and what is happening. Isobaric, isochoric, adiabatic, isothermal. Easiest one is adiabatic. Adiabatic means heat will be zero, obviously. Okay. Next, let's go to isochoric, because in isochoric, work done will be zero. So work done is zero. Whatever heat is there will go in delta U. So isochoric is basically 2 because work done will be 0. Okay. Next, we can go to isothermal. In isothermal, delta U is 0. So I think this is the right answer because delta U will be 0. So Q will be work plus delta U. Delta U is not there. All the heat went in work. Last one over here is basically isobaric. So here all the things will be there. So isobaric is basically fourth. So is there an option which matches with everything, guys? Check it out. A is going with 4 in these three places. B is going with 2. B is going with 2. So I think the third option is the right one. The third option, that's how you do it. Yes, perfect. Amazing, 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 amazing. Very good. Very good. Awesome. Let's go to the next question coming up on your screen. And here it is. An ideal gas exists in a state where the pressure volume is isothermally expanded to 4 times its initial volume, then isobarically compressed to original volume, then final system is heated isochorically to bring it to its same state. The amount of heat exchange in this process is. In such questions, better to draw the diagram of what is exactly happening so that you get a good idea of this processes. So this is pressure, this is volume. It exists in a state of pressure and volume P naught and V naught. So let's call this as P naught. Let's call this as P naught and this as V naught. Okay. Now you are taking it isothermally. It is isothermally expanded to 4 times of its initial volume. So that is the first thing. Then isobarically compressed. Okay. So I'll do one thing. Isobaric process is there, which is compressing it. Perfect. Compressing it isobarically. Okay. And then isochorically to its initial state. So I think this is what it should look like. And then this is your P naught. Yeah. And this is your V naught. So this is isothermal expansion. Can you see? Isothermally expanded to 4 times its initial volume. So this is 4 times of V naught. Then isobarically compressed to its original volume and then taken to its initial state via isobaric or sorry isochoric process. This is what the system looks like. Processes look like. Now, once the diagram is done, let's do it one by one, guys. Some things are very obvious. Like, say, for example, if I mark this point as 1, this is 2, and this is 3. From 3 to 1, it is isochoric. 3 to 1 is basically isochoric process. So, therefore, work done from 3 to 1 will be obviously 0. That is very straightforward. Next thing, from 2 to 3 is also slightly easy, but only problem is I do not know the pressure over there. So I need to first of all figure out how much pressure is there. But think about it, it is given that it is isothermal process. It is clearly given that it is isothermal process from 1 to 2. So if you actually think about 1 to 2, 1 to 2, which is isothermal process, P1 V1 will be equal to P2 V2. P1 is P naught, V1 is V naught, P2 I do not know, V2 is V naught into 4. It is 4 times of V naught basically, right? It is 4 times of V naught. So therefore, the last pressure is P naught divided by 4. V naught goes, 4 comes below. So the final pressure over here, is P naught divided by 4. Now I think we can easily figure out how much is that isochoric process work done. So from 2 to 3, it is not isochoric, isobaric work done. 2 to 3 is isobaric. So work done in 2 to 3 will be pressure, which is P naught by 4 into the volume. Volume is final minus initial, so V naught minus 4 V naught, which makes it 3 P naught V naught divided by 4, which gives me minus 3 P naught V naught divided by 4. So that is work done from 2 to 3. That is also done. Now the last part remaining is for 1 to 2. How much is the work done? So work done from 1 to 2 will be nRT log V2 by V1 or P1 V1 into ln V2 by V1. That's the formula. So initial pressure, initial volume log of 4 V naught by V naught. So it will be P naught V naught log 4. That's it. Now comes the final answer, whatever we have to give. So the final answer, guys, the final answer of the total work done 1 to 2, it is P naught V naught log 4. Then 2 to 3, it is minus 3 by 4 P naught V naught. From 3 to 1, it is 0. So that is the answer. But what we can do, we can write log 4 as 2 log 2. So 2 P naught V naught log 2 minus 3 by 4 is basically 0.75, and this will be P naught into V naught. So this would be the answer. Where is 2 P naught, 2 log 2 and 0.75? That is over here. That is option 1. Option 1 is the right answer. Yeah, everyone? Pakka? Very good, guys. Let's go to one more question coming up on your screen. And here it is. What does it say? It says a monoatomic gas, just 5 more minutes, and then I think Diksha ma'am can begin. I'm pretty sure she will be also waiting. Yeah. So Diksha ma'am, if you are listening, just give me 5-10 minutes and then maybe you can begin. Yeah. Monoatomic gas having 5 by 3 gamma is stored in a thermally insulated container and the gas is suddenly compressed to 1/8 of its volume. The ratio final to the initial pressure is how much? Pressure, volume, adiabatic. Why adiabatic? Because thermally insulated means it is adiabatic process. And the moment adiabatic process is there, pressure and volume are being discussed. I will start thinking about P1 V1 raised to gamma will be P2 V2 raised to gamma. PV raised to gamma is constant. So P1 I do not know, volume 1 I do not know, gamma is basically 5 by 3, just put it as it is. P2 I do not know, final volume I know is 1 by 8 of the original volume, so V1 by 8 and the whole thing raised to 5 by 3. The question is ratio of final to the initial pressure, so P2 by P1 is asked. So P2 by P1 is asked. So P2 by P1 will be, so if you take P1 down, this term will go below V1. So V1 raised to 5 by 3, whole thing divided by V1 by 8, whole thing raised to 5 by 3. This will become V1 raised to 5 by 3 and V1 raised to 5 by 3. Obviously, that 8 raised to 5 by 3 will go on the top. Both of them will cancel. So this 8 is nothing but 2 raised to 3, whole thing raised to 5 by 3. That 3 and 1 by 3 will cancel, it will become 2 raised to 5. So 2 raised to 5 is nothing but 32. So 32 is to 1 will be the answer, which is the third option, which is nothing but the third option. Very good. Oh, Ak, you are in the 8th standard. My goodness, man. Crazy. Now, the last type of process which you should be aware of is the polytropic process. Basically, it is a generalized process wherever you see PV raised to some real number n is a constant. Now, if you think logically, if that value of n is 0, well, volume raised to 0 is 1. So, pressure will be constant. It will become isobaric. Similarly, if n becomes 1, then it becomes isothermal because pressure into volume will be constant. If n becomes gamma, it becomes adiabatic. If n becomes infinity, it becomes isochoric. So a very generic process wherever pressure into volume raised to some power of n is constant, that is a polytropic process. And in any such polytropic process, right, you can put some special values and make it isobaric, isothermal, adiabatic or isochoric by choosing suitable values of n. Okay. Now, what about all the terms like heat, delta U, etc.? Delta U is always NCV delta T. Let me put that over here. All these formulas might look little bit confusing at times. This and all not needed. All this not needed. This is anyways valid. So, delta U is always NCV delta T, non-negotiable, no matter what you do. Work done, instead of, see guys, in that, where is it? Adiabatic formula. Instead of putting P1 V1 minus P2 V2 by gamma minus 1, what I will do, because in adiabatic process PV raised to gamma was a constant, replace that gamma with that number n, I will get n minus 1 over here. So P1 V1 minus P2 V2 by n minus 1. That's it. That is the formula. That's how you can easily remember it. P1, I'll just put it over here. P1 V1 minus P2 V2 upon n minus 1. That's it. That is the answer for the work done. From this delta U and work, you can find out the heat. Because delta U is here, work is there. You can find out how much ever heat was involved in that polytropic process. So only remember these two things. Delta U is anyways always NCV delta T. Work done is just like for adiabatic process, just that wherever gamma was there, replace it with N. Because even for adiabatic, it was PV raised to gamma. So replace that gamma with N, you will get the same looking formula. Okay, great. So let's see if you can figure out one of that kind of questions. The pressure and the volume are related by PV raised to 3 by 2 is some constant. The work done when the gas is taken from this state to this state is how much? Simple, easy peasy question. This is first of all a polytropic process because PV raised to something is constant. Here n is 3 by 2. That power is 3 by 2. Great. So work done is nothing but P1 V1 V1 minus P2 V2 upon n minus 1. N is basically 3 by 2 minus 1. So it will become P1 V1 minus P2 V2. 3 by 2 minus 1 is 1 by 2. So that 2 goes on the top. So 2 into P1 V1 minus P2 V2 is the answer. 2 into P1 V1 minus P2 V2, which is option number 1. Options look very, very similar and confusing. And it is such a straightforward question if you just know how exactly to use the formula. This came in 2025. So remember, formulas are simple, concepts are simple. Okay, the only part is where you can get confused, you can get blanked out, you don't remember how exactly to be used. That's where you are going to lose marks. So please avoid such things. Okay, great. Last question on your screen, and then we are done. The ideal gas is given by this equation, the coefficient of volume expansion, separate chapter combined with this chapter. Volume expansion, thermal expansion, separate chapter. PT raised to 3 is constant, is polytropic process. But you will be like, sir, volume is not there. Don't worry, I will make it in terms of volume. PT cube is a constant, right? I can write pressure into volume is nRT, right? So what will my temperature be? temperature will be PV divided by NR. So I'm just going to put, instead of temperature, pressure into volume divided by NR, and this whole thing will be cubed, and this is pressure and this is constant. All right, so we will have P multiplied by P cube multiplied by V cube. Is NR is a constant, so bring that over here. It's a new constant. It's a new constant. So we'll have P raised to 4 multiplied by V cube is basically a constant. Yeah, is that right? But we cannot stop over there. We have to do something with it. We have to do something with it. Can I get thermal expansion answer with pressure and volume? Can I get thermal expansion answer just with pressure and volume? No, that I will not get. So doing this will lead us nowhere. Lot of people just substitute temperature and try to get in PV raised to gamma form, and they feel that they will get the answer, but that is not true. I want coefficient of volume expansion. So this will not give you the answer just because you have got it in the polytropic form. Rather think like this. For volume expansion, what do we need? The change in the volume, which is basically delta V, is original volume gamma into delta T. So we want basically delta V by delta T, delta V by delta T into 1 by V. That is what is going to give me gamma. So gamma is specifically dV by dt and into 1 by V. Oh, I need dV by dt. So I don't want pressure actually. Oh, so I will write pressure is nRT by volume, and I will put, instead of pressure, nRT by volume as it is, and into T cube is a constant. So we will have T raised to 3 into V raised to -1, or you can just shift it on the other side. This constant divided by nr into volume. This is the new expression that I'm getting. Now differentiate both sides with respect to some variable. Let's say dt cube by dx is equal to constant. Forget it. Okay, it's some constant. You can just put it as k, and you will have dv by dx. This can be used, written down in form of chain rule. So dt cube pi dt into dt by dx is equal to k into dv by dx. Now what you do is cancel this dx from both the sides. See what do you get now? Derivative of t cube is basically 3t square. This you have dt as it is, and here you have k into just dv. Now if you rearrange it slightly, you will get dv by dt. dv by dt is nothing but 3t square by that constant. 3t square by our constant. Is that right? So now I think we are in a position to get gamma. So gamma will be dv by dt, which is nothing but 3t square divided by that constant. But what is volume? So for that, again go over here. If you go back into this particular equation, you will see that T cube was that constant into volume. So volume was T cube by the constant. T cube by the constant. So put T cube divided by the constant was volume, but 1 by V is asked. So there will be T cube here and K on the top. K will get cancelled off. K and K will get cancelled off. T square and T square will get cancelled off. So I'll get 3 by T as my gamma. So gamma is 3 by T, which is the fourth option. So this kind of question also has come in our JEE Mains. So first I thought, for volume expansion, what is the expression and what is gamma exactly? So from that I understood I need a relationship between volume and temperature. So I got rid of pressure using ideal gas equation. Once I did that, I got an expression, and then I saw, since I need derivatives or deltas, so I took derivatives on both the sides and used mathematics to finally get the answer. Okay, that's all that is there in today's session. I hope you enjoyed it. The PDF will be available by tomorrow. Keep liking, keep taking up these classes. These are short, crisp classes for your revision. and this will give you that final blow, that what you need for that leg of preparation for the last 2 months. Okay, so chemistry is going to start and maths after that. Attend every single class, and do not forget 5th November 6 o'clock, your launch is going to be there on this particular channel. Have a great time. Do not forget to like. Bye bye. Take care.